Hello and welcome to Prepspot. In this video, we are going to know about some fascinating insights into a critical area of research that concerns not only our understanding of Earth's magnetic field but also the future of space technology and satellite operations. What we are focusing on today is the South Atlantic Anomaly, or SA, a region of Earth's magnetic field located over South America and the Southern Atlantic Ocean. Historically, this area has been known to be a place where the magnetic field is significantly weaker than in other parts of our planet. In simple terms, imagine our planet is encased in a magnetic shield that protects us from harmful solar and cosmic radiation. However, the SA is like a thinning patch in that shield, which means that more radiation is able to penetrate closer to Earth's atmosphere in that specific region. Over the past few decades, scientists have been observing the characteristics of the SA with keen interest, primarily because the anomaly has important implications for satellites and space missions that traverse this area. Research now suggests that this weak spot is not only persisting but may also be evolving in an unexpected way. NASA's latest models indicate that the anomaly is likely to split into two distinct regions by the year 2025. This prediction stems from detailed studies of how the Earth's magnetic field is behaving, a phenomenon largely driven by the dynamic processes occurring deep within the Earth's core, where the constant movement of molten iron generates our planet's magnetic field. This evolution is nothing new, and scientists have been aware of it for a long time. There is some sensational reporting that labels it as a hole in the magnetic field, but it's important to clarify that this is more a reflection of media dramatization rather than a discovery of a new phenomenon. Instead, what we are witnessing is the natural progression of a known irregularity that has long existed. What makes the SA particularly noteworthy is its potential impact on satellite operations. Satellites orbiting Earth frequently pass through this region, and in doing so, they are exposed to heightened levels of radiation that can lead to interference in their electronic systems, data corruption, or even temporary shutdowns of sensitive instruments. For instance, the International Space Station and numerous communications and research satellites are particularly at risk. The heightened exposure to solar particles and cosmic rays necessitates that space agencies like NASA and the European Space Agency continuously adapt their strategies for mitigating these effects. Engineers and mission planners now face the challenge of ensuring that satellite instruments can withstand this increased radiation. This might involve using improved shielding materials or adjusting the operational schedules of sensitive equipment when a satellite is scheduled to fly through the anomaly. The possible splitting of the SA into two regions could introduce additional complexity to these mitigation strategies by altering the geography of the radiation exposure zones, making the predictive modeling and planning for satellite missions even more critical. It is also worth mentioning that the current changes in the SA have sparked a lively debate in the scientific community concerning their broader implications, particularly regarding the natural cycle of Earth's magnetic field. One camp of researchers sees these changes as part of the natural variation and slow evolution of our magnetic field, a process that repeats over hundreds of thousands of years. In this view, the splitting of the SA is simply an expression of the dynamic nature of Earth's geodynamo, the process that generates the magnetic field as molten iron moves within the planet's outer core. This phenomenon is closely linked to the phenomenon known as magnetic pole reversal, a process in which the north and south magnetic poles gradually switch positions over geological timescales. Although the splitting of the SA by 2025 might hint at underlying shifts in the magnetic field, experts caution that we should not jump to conclusions about an imminent reversal. Instead, these changes are more likely to be part of the normal ebb and flow of Earth's magnetic dynamics. On the other side of the debate, some scientists stress that while the variations in the SA are natural and have been observed for decades, the potential for significant technological disruption is real and must not be underestimated. They argue that even small increases in radiation exposure can have outsized impacts on the high-precision instruments aboard satellites. To give you a bit more context, the SA was first identified during the early days of space exploration in the 1960s when satellite missions began detecting unusual levels of radiation over this part of the globe. These initial observations paved the way for decades of continuous monitoring and have given us a robust framework for understanding how and why the anomaly behaves the way it does. Over time, sophisticated instruments aboard satellites like NASA's magnetospheric multiscale mission and the European Space Agency's SWARM mission have provided researchers with a wealth of data, allowing us to build detailed models of the magnetic field's structure and predict its future evolution with increasing accuracy. These models rely on both direct measurements of the magnetic field's strength and on computer simulations that incorporate the known physics of Earth's core dynamics. What emerges from these studies is a picture of an ever-changing, living planet whose magnetic shield is far from static. While the potential splitting of the SA has generated headlines and raised concerns among satellite operators, it is important to underscore that this phenomenon poses no direct threat to life on Earth. The effects of the anomaly are confined to the near-Earth space environment. On the ground, we are protected by the overwhelming strength of the Earth's magnetic field in other regions, and the variations observed in the SA are simply part of the normal geographical diversity of that field. That said, the implications for space technology are significant. Every time a satellite passes through the anomaly, it faces a temporary risk of exposure to high-energy particles that could cause malfunctions or degrade its operational lifespan. This is why space agencies are diligently testing and refining new technologies to ensure that their satellites can not only withstand these exposures but continue to function reliably even in challenging environments. Looking at the broader picture, the current research into the SA is emblematic of how scientific inquiry frequently drives innovation in technology and enhances our understanding of natural processes. As scientists continue to refine their models and gather more data, we stand to gain valuable insights into the underlying mechanisms that control Earth's magnetic field. This research not only benefits space agencies but also informs other areas of study, including climate science and geophysics. For example, understanding how the magnetic field changes over time can help improve our predictions regarding space weather events such as solar flares and geomagnetic storms, which can have cascading effects on power grids and communication networks here on Earth. It's a reminder that even phenomena that occur hundreds of miles above our heads can have far-reaching consequences. As we peer into the future, we see that the evolution of the SA is part of a larger and immensely complex story about the dynamic processes occurring within our planet. The splitting of the anomaly, predicted to occur around 2025, may very well be a natural event, but it comes at a time when humanity's reliance on satellite technology is greater than ever. Our modern world depends on these technological assets for everything from weather forecasting to international communications, navigation, and even financial transactions. With satellite networks forming the backbone of our digital infrastructure, any increase in risk, even a modest one, must be addressed proactively. Agencies such as NASA, ESA, and several private aerospace companies are thus working in tandem to develop more resilient systems. They are conducting numerous tests, reviewing radiation shielding technologies, and studying the interactions between charged particles and onboard electronics to mitigate potential disruptions. In many ways, this ongoing research is similar to how we prepare for natural hazards on Earth, taking a precautionary approach to minimize impacts even when we know that such events are part of our natural environment. Indeed, the discussion surrounding the SA also brings up an important point about public perception and scientific communication. With terms like hole in the magnetic field being used in some media reports, there is a risk of misinterpretation. It is essential for us, whether we are educators, scientists, or simply informed citizens, to understand that while these terms can capture public attention, they often simplify the underlying science too much. The reality is much more nuanced. The SA is not a mysterious void or an entirely new anomaly, it is a manifestation of the natural variability in Earth's magnetic field. As scientists continue to monitor and analyze it, we are reminded that the Earth is an active and dynamic system, constantly evolving over time. And while these changes might spark questions about things like magnetic pole reversals, experts caution us to view such phenomena within the context of long-term planetary processes rather than as immediate indicators of catastrophic change. So, what does all of this mean for our future in space and the evolving relationship between technology and nature? In many ways, it highlights the intertwined nature of scientific research and technological advancement. As we learn more about the SA, we are better positioned to design satellites that can operate safely and efficiently even in regions where the radiation environment is more hostile. In turn, these improved technologies enable us to collect more precise data about our planet's magnetic field, thereby creating a feedback loop of discovery and innovation. It is both an exciting challenge and a critical opportunity for those involved in space exploration and satellite technology. Whether you are an engineer tasked with designing the next generation of satellites, a scientist working on unraveling the mysteries of Earth's deep interior, or simply someone fascinated by the dynamic forces at play in our universe, the evolution of the South Atlantic anomaly is a subject that touches on multiple facets of modern science and technology. As we wrap up today's session, I encourage you to consider the broader implications of this phenomenon. The weakening and potential splitting of the SA serve as a powerful reminder that the environment in which our technology operates is rarely static. It is subject to a host of natural variations and processes that can influence everything from the reliability of communication networks to the success of exploratory missions far beyond our home planet. At the same time, the ongoing debate among experts about whether these changes might eventually herald a magnetic pole reversal or simply represent another chapter in the story of Earth's magnetic field underscores the inherent complexity and unpredictability of the natural world. It is a field that continues to evolve, with each new discovery prompting further questions and research. In many respects, the study of the SA encapsulates the essence of scientific inquiry, an ongoing pursuit of knowledge where each answer leads to new questions, and every new discovery builds on the foundations laid by previous generations of researchers. Today, as we stand on the brink of potentially transformative changes in our understanding of space weather and Earth's magnetic environment, it is clear that our continued exploration and study of these phenomena are not only important for scientific advancement but also for the practical management of the technological systems we rely on so heavily. The predictive models and detailed measurements generated by satellites are invaluable tools that enable us to forecast potential disruptions and devise strategies to counteract them. It is a testament to human ingenuity that we can monitor such distant and dynamic processes with such precision, and it reminds us of the incredible capabilities of modern scientific instrumentation and computational modeling. As research continues and we approach the predicted timeline for changes within the SA, collaboration between international space agencies, academic institutions, and private sector companies will be more critical than ever. This collaborative effort is helping ensure that despite the natural challenges posed by our planet's complex magnetic environment, our technological infrastructure remains robust and resilient. In summary, the South Atlantic anomaly is a long-known feature of Earth's magnetic field that is undergoing further evolution, with current predictions indicating that it may divide into two separate regions by 2025. This occurrence, while sounding alarming in some of the headlines we've seen, is a natural process linked to the dynamic behavior of Earth's molten core and the fluid nature of the geodynamo. It poses tangible challenges to satellites and space missions by increasing their exposure to radiation, a problem that requires ongoing refinement in engineering and operational protocols. Yet, these changes are not a cause for panic among those of us living on Earth. Rather, they represent an important aspect of how our planet operates and evolves. By staying informed and proactively adapting our technology, we can mitigate the risks and continue to explore and understand both the near-Earth space environment and the broader cosmos. Answer this question in comments. The correct answer will be given hot and pinned. Lastly, we just want to let you know that we are a newly emerging online platform for competitive exams. Creating educational explainer videos like these requires a lot of effort, money, and time. If you like these videos and want us to excel and create videos in all categories of competitive exams, then you can consider supporting us with a one-time donation through the Ko-fi platform and also by becoming a member through Patreon. This will help us create more such informative educational videos in the competitive exams space. So, one last time, subscribe and share this channel with all your friends who are preparing for competitive exams. And also, follow us on social media platforms. The links are given in the About section of the channel and also in the video description. So, see you in the next video.